Hello, science students. Welcome to today's lesson about our solar system, gravity, and orbits. You recall that we began this unit learning about what people used to believe, and that was that the Earth was at the center of our solar system and everything else, the sun, the moon, the stars, other planets, all revolved around Earth. It wasn't until Nicholas Copernicus ended up publishing his work, his diagram, his data to prove and support that idea that it was actually the sun that was at the center of the solar system. He called that model the heliocentric model. And that word heliocentric literally means sun at the center. And it's that representation of our solar system with the sun at the center, planets and everything else revolving around the sun. We found that besides the sun and the earth, there's several other things that help to make up our solar system that include the sun itself, those planets like Earth that we mentioned. There's also items that we call dwarf planets, as well as asteroids and comets. Of course, there are some other items found in our solar system that we won't cover in this lesson. It's important to remember that there are other things that don't fit these categories that occur in our solar system, but for our purposes, we're going to focus on these. First up is the sun, which is a star. Just like all of the other stars you see up in the sky at night, our sun, though, is so close to us, we see it as the sun as opposed to a speck of light at night. Our sun is in a category of stars called a yellow dwarf, and out of the different types of stars, I believe there's 7 different types of stars, a yellow dwarf is just on the small side of middle. It is very, very massive, though. It's made up primarily of hydrogen and helium, but we believe there's small amounts of oxygen, carbon, neon, and iron in there as well. The sun is so massive, it's hard to really put a scale to it. But a few comparisons include that it's about 333,000 times the mass of the Earth. Remember, mass measures how much matter there is. So if you think about all the matter that makes up you and me, the air, the oceans, the sea, the layers of rock, the layers of our planet, its core, its atmosphere, everything, all of the stuff inside of Earth. You took Earth and multiplied all of that matter by 333,000 times, and you'd have the mass or the amount of matter in our sun. Or if you think about distances a little bit easier, remember spheres have a radius and a diameter. The diameter of the sun is roughly 109 times the diameter of Earth. Like I said, these are huge measurements to try to understand. The diameter of the sun would be something like 864,000 miles. If you think about what 1 mile is, it's really hard to comprehend and think about 864,000 miles. Very, very, very large. It's so large, in fact, that it's got really, really high amounts of heat and pressure. With that much material all being pulled towards the center of the sun, it causes a great deal of heat and pressure. This heat and pressure creates what we call nuclear fusion to occur. In nuclear fusion, 2 nuclei get forced together and join to create a different element. This is different than a chemical bond, where the individual atoms stay the same and they get joined together. This is actually smashing together the nucleus of the atom so forcefully that they stick together and create a new and different element. In this case, we've got 2 hydrogen atoms combining together. They join together and form 1 helium atom. Nuclear fusion reactions are what actually create the infrared and visual light that we get from the sun. All of that energy that's transmitted by infrared waves and visible light waves comes from the process of nuclear fusion inside of the sun. On Earth, we've played with the atom a little bit, and we use nuclear fission, where we split the atom's nuclei apart to create nuclear energy or atomic bombs. Exact opposite process of what's happening inside of the sun. To be considered a planet, an object in our solar system must revolve around a sun or orbit a sun, a star. It must also have a spherical shape or really close to spherical shape. And this is because it's got enough mass that its own gravity pulls everything in on it forcefully enough that you end up with a nice circular spherical shape. It also has to have cleared the neighborhood. And this in astronomy means that along its orbit, it's cleared out, collided, and bumped out or fused with all of the other materials in its orbit. It's kind of swept up all of the other debris and items that were in its path. And then, of course, it also has to be the largest object in its path, or really, really close to its orbital path. If there are some other objects that are really close, and for instance, their orbits might overlap at times, then you end up with two different objects that share parts of an orbit, and it may not technically have cleared its neighborhood. We have found that this definition, these characteristics of a planet, we have 8 different objects that fit that, including Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. A good way to recall these is a mnemonic device where the first letter of each word is the first letter of each word in a sentence. So, for instance, Mercury starts with the letter M. The first word in our mnemonic device starts with the letter M. If you can remember, my very educated mother just served us nachos, you have all 8 planets in order from closest to the sun to farthest away. Those 4 planets that are closest to the sun are called inner planets. They're inside this unique feature of our solar system that is a ring of kind of space debris that we call asteroids. There's an orbit of all these tiny, different sized objects. And inside there, we find 4 inner planets. These are relatively small when compared to the outer planets, or the ones on the other side of the ring. They include, though, Mercury, Venus, Earth, and Mars. These planets are sometimes referred to as terrestrial planets because they're made out of rocky materials. Terra is a root word that means earth or rock or dirt. So terrestrial means rocky planets. We mentioned that there were inner planets, and so logic would tell you that there should also be outer planets. And these are found beyond that ring of space debris we call asteroids. These are very, very large in size when compared to the inner planets, and are sometimes called giants. They include Jupiter, Saturn, Uranus, and Neptune. It's important to remember that these pictures in the presentation are all the same size, but the planets themselves actually differ in size, and so these images are not to scale. These giant planets are primarily made out of gas and ice, and so we refer to them as gas giants. There are some objects, though, that fit a lot of the definitions of a planet, but not all of them. And we call these objects, especially those ones that have a larger or a smaller mass than the other objects near or crossing its orbit, are called dwarf planets. A few years back, the International Astronomical Union, a collection of space scientists, got together and someone proposed a change to the definition of a planet. Based off of their research, their documentation, their evidence, they said we should be calling planets by this new definition. And when they changed that definition, Pluto got reclassified as a dwarf planet. Several other objects also got reclassified when we changed the definition of a planet. But it's important to remember that these changes happen in science all the time as we develop better theories, better understandings, new data, new technologies, better measurements. We revisit our understanding and tweak them with the new information. Just like we used to have an understanding of the solar system with the Earth at the center, when we gained better information and a better understanding, we changed our beliefs to reflect that new knowledge. Unfortunately, Pluto, poor Pluto, got kicked out and lost its status as a full on planet and is now considered a dwarf planet. Besides planets and dwarf planets, there are also lots of other objects that orbit the sun. Ones that are rather small and rocky are called asteroids, and these are found in between the orbits of Mars and Jupiter. These asteroids generally aren't large enough to have a gravitational field that creates their spherical shape. Some are, but generally speaking, they are not. There's also a unique item called a comet. Comets differ from asteroids because they're more gaseous and made of dust and ice as opposed to solid rock like asteroids are. And then comets also tend to have their own orbit, where asteroids are all generally kind of in the same area together in what we call the asteroid belt. These comets kind of each have their own independent orbits. But as they orbit, because they're made of gas and dust, parts of them kind of fall off and are left behind. And this creates a really unique, neat, glowing tail that follows behind their movement. On Earth, we measure distances with things like inches, feet, and miles. Or in science, we use centimeters, meters, and kilometers. Those values are so small in comparison to space, though. The number of kilometers or meters or feet or miles is so large, it becomes hard for us to process and understand and actually be able to comprehend. So instead, we've created a distance measurement called the astronomical unit. It's abbreviated with AU, and it's equal to the distance between the Earth and the Sun, which is roughly on average about 150,000 kilometers. In this case, as we as humans created a new measurement tool, we made it all about us. An astronomical unit, the unit we use to measure distances in space, is equal to the distance between Earth and the Sun. You can see here some different measurements for each planet, both in kilometers and AUs, or astronomical units. You see that Earth is 1 AU. All of those planets closer to the Sun than Earth have a distance of less than 1 AU. Mercury is about 4/10, Venus is about 3/4 of the distance to Earth, Mars is about 1.5 times. And as you get much further out, you see that Uranus and Neptune are about 20, 30 different times as far away from the Sun as Earth is. We also describe planets, besides being how far or close to the Sun they are, with measurements like the period of revolution and the period of rotation. In this instance, the period of is referring to the amount of time. So the time it takes to revolve or the time it takes to rotate. Rotation and revolution sound very similar, but they're describing two different things. For instance, the period of revolution is the amount of time it takes to complete a lap around the Sun. One full orbit around the Sun is the period of revolution. Here on Earth, that's equal to about 1 year. The period of rotation, though, is the time it takes to make one full spin around an axis, or 360 degrees of rotation. On Earth, that's roughly 24 hours or 1 day. Here in this image, you can see a rotation. The Earth is spinning around 360 degrees around its axis. This example is showing you a revolution. one full orbit around the sun. Here you can see them both next to each other. Rotation is spinning along the axis. Revolution, the entire thing is circling another object. Copernicus was lacking this idea of gravity to explain what held stuff together and why things didn't go flying off. He discovered and described gravity as the universal force of attraction that acts between all matter. That includes matter here on Earth, like you throw a ball up into the sky, it gets pulled back and attracted back down to Earth. You jump, you fall back down to Earth. These same principles apply to things in space as well. Back when we completed our simulation, you were able to identify two key patterns about gravity. Those included that when the mass is greater, the force of gravity is also greater. If you think back to the mass of the sun being 333,000 times the mass of the Earth, we're talking about a really massive objects. And so they have a stronger gravitational pull. Same type of thing when it comes to distance. As distance changes, so does gravity. As the distance between two objects gets larger or increases, gravity's force gets smaller or decreases, and vice versa. As two objects get closer together, gravity pulls on them stronger. These two things help to change the gravitational forces in our solar system. But the interaction of gravity between the sun and other objects is what creates things orbiting and keeps them orbiting. Objects that orbit the sun start out with a velocity. They start moving in a straight line. As they come close enough to the sun, their distance gets close enough that gravity is strong enough to capture them. The sun's gravitational pull starts to pull the object towards the sun. This changes the direction of its motion. If you remember Newton's first law of motion, objects at rest remain at rest, and objects in motion remain in constant motion until a force acts on them. That force of gravity starts to act on that object's motion and changes it into a circular pattern, which you can see in this example here. Orange line is showing the pull of gravity. The green line is showing that original direction it would be traveling. And then the blue is the combination of the two. That's the orbit or the path. Just as we learned in Newton's laws that forces can either add or act against each other. In this case, the combination of those two forces end up creating that circular orbit. It's important to remember that idea about distance as well. How close a planet or an object is to the sun affects its orbit. Items that are farther away orbit much slower. Objects that are closer orbit much quicker. For instance, Jupiter is about 5 AUs away from the sun, or about 5 times as far away from the sun as the Earth is, but its period of revolution is about 12 times longer than Earth, which would be about 12 years on Earth it would take to make one full revolution. We'll deal a little bit more with those patterns in gravity with mass and distance, how they affect gravity, as we learn more about our specific Earth, Moon, and Sun interactions later on in this unit. Thank you for your time. I hope you have a wonderful